In this lecture, we want to see how the arithmetic operations are implemented in the ALU of 8085 microprocessor. So the goal of these operations include addition, subtraction, increment, and decrement. What is the addition? Well, we know that if we want to add one bit with another bit, the state of every bit would be either 0 or 1. So 0 plus 0 is 0, 0 and 1 would be 1, 1 and 0 would be 1, and 1 and 1 plus 1 is equal to 2. But 2 cannot be fit in 1 bit. So the result has to be 2 bit because 2 is represented using 1, 0 in binary. So to show or to hold the result of the addition of one bit with another in the binary, we need at least 2 bits to cover all the different states. Therefore, we use 2 bits to hold the result. 0 and 0 would be 0, 0, 0, 1 would be 0, 1, 1, 0 would be 0, 1, and 1, 1 is 1, 0. We could show it in another way. We have one bit to add with another bit. We have 4 different states. This would be the result of the left bit, and this would be the result of the right bit. If we look at them and pay attention, we see that we have two truth tables. One of them is the truth table of the AND gate, and another is the truth table of the XOR gate. So we could just put them together, XOR gate and AND gate. The combination of an AND and a NOT is just an AND gate. So this AND gate would give us the left bit, and this one would give us the right bit. So whatever combination we use for our inputs on these two wires, it is either 0, 0, 0, 1, 1, 0, and 1, 1. This block would give us the left bit, which would be either 0 or 1, and this block would give us the right bit depending on the combination of two inputs. But we have a problem here. First of all, as an example, if we give 1, 1, then the AND gate here would give us 1, and the XOR, because they are both the same, the inputs of the XOR based on the truth table of this XOR gate, we would have 0, 1. So since we are looking at this as the left bit, we would have 1, 0 as the result. This is the right bit, this is the left bit. But we have a problem. Like, as an example, you might think if we had several of these blocks alongside each other, we could just add any two numbers with one bit added to another. Like, imagine right now that we are adding 0, 1, 1 to 0, 0, 1. So one thing that might come to your mind is that we copy paste this block 3 times, and then we say, well, one bit is added with another bit in the first block, these 2 bits are added in the second block, and so on. But let's see the problem. If 1 and 1 are added, we know that the result would be 1, 0, but 1, 0, based on this, 1, 0 cannot be fit in one bit, right? So we say this would be 0. Let me change the color. So it say this would be 0, and 1 would be carried out in the next stage. And then you would have 1, 1, and 0. Again, 1 and 1 would be 1, 0 plus 0 is still 1, 0. So you would have 0, and another 1 would be carried into the next stage, and 1, 0, 0 would be equal to 1. So this is 3, and this is 1. You would have the result 4 in the decimal. So as you see, in each stage other than the first one, we are adding actually 3 bits or 3 inputs instead of the 2. So what you could say is that when we are adding one number with another or one bit with another bit, we are actually adding 3 bits. The only thing is that this carry bit for the first stage is equal to 0. So you see, if we say this thing, if we say that at each stage when we are adding one number with another, we are actually adding 3 bits with each other. In this way, we would have 0, 1, 1. At the first stage, we always say this is 0 because it hasn't been carried out of any stage. The first stage is just the beginning. We have just started the first stage. So this would be 0, 1, 1 would be equal to 0, 1, then we have 1 here. Again, if we have 3 inputs, 1 and 1 would be 0, another 1 here, 1, 0, 0, and we have 1 here. Now, we might have a carry of 0 in the next stage. Still, we have 3 inputs for all of them. So because of this problem and the fact that the adder that we have implemented only has 2 inputs, we can't put them together to add a multi-bit value. Instead, we use another circuit like this. So if we just we could just prove that as I said, I've created another course which in that everything has been explained in more detail. This is just a more like a review over how to implement the addition in the ALU. But let's say that I'm telling you that this circuit, we have three inputs. This would be A, this would be B, and this would be the carry in, which we just make it equal to 0. And I'm telling you that if we put multiple of these blocks alongside each other, 8 of them, then we could add an 8-bit value with another. Now let's see if we could just actually do some addition, do some example to see this circuit works. As an example, let's say I have this value and also this one. We want to add them together. So you could just look in the binary. This would be equal to this is 128 plus 2 plus 1, which is every one of these has a value, right? This would be 131, and this is 128 plus 8 plus 4 plus 1, well, which is 12, 13, and this is just 141, right? So we want to add 131 with 141, which obviously the result should be 272. So 272 cannot be fit in 8 bits, because using 8 bits we could only show 2 to the power of 8 equal to 256 different states from 0 to 255, right? But we want to see if we are adding this value with this one, we actually get the result of 272. And I'm telling you that this would work. Now, how would we add these two numbers? We say this is the least significant bit of the value of A, and this is the least significant bit of the value of B. So I just write the least significant bit of A here and B here. Both of them are 1. Then the next significant bit, the next least significant bit is this one for the A. So I write it here, and for B I have 0. Then I have 0 and 1 for A and B respectively. So I would have 0 here and 1 here. After that we get another 0 and 1, and we just write them down until we just get to the most significant bit. So I've just written all of the values here to see if we could actually follow along different wires to see this circuit works and it could accomplish the adding. So I want to change the color to red. So if we have 1 1 in the first stage, we would have 1 1 in the, and the only thing that you need to know is actually the truth table of these two circuits, because everything has been made using this XOR. This is its truth table. The output is 0 if both inputs are equal, and this is the truth table of the AND. So if we have 1 1, we have 1 1 at the inputs of XOR. Based on its truth table, we would have 0 here. 1 1, we get 0. This 0 would go as the inputs, one of the inputs of the AND, and we said that the carry in, that the carry of the first stage would be equal to 0. You would always make it equal to 0 because it is just the first stage. So this 0 would go to the other input of this NAND gate, this AND gate, the combination of a NAND and NOT, and you would have a 0 here. Obviously we have A and B directly to these two AND gates. Both of them are 1, so you would have 1 here. 0 and 1 in the XOR gate would give us a 1. Here we have a 0 through this wire, and we have a 0 here. 0 and 0 would give us a 0. This 0 is the rightmost bit of our result. So I say in my result this would be equal to 0. This is the least significant bit of the result. But what about this? Well, this would be carried out onto the second stage, acting as the carry in of this stage. So we would have a 1 here. This one would go through the XOR gate, also through this block of the AND gate. We also have a 0 here and a 1 here, which the AND gate would make them equal to 0. Then we also have 1 and 0 in the XOR gate would give us a 1. This 1 would go through the AND gate. Since both of them are equal to 1, we would have a 1 here. 1 and 0 based on the truth table of the XOR gate would give us a 1 because they are different. We also have a 1 and 1 on the inputs of this XOR gate. Because they are equal, we would have a 0 here. This 0 would be the next bit of our result would be equal to 0 here. But what about this? This would be carried onto the next stage. Again, we have a 1 here. This we have a 0, 1 on this XOR gate, giving us a 1 because they are different. 1 and 1 would give us 0 because they are equal to each other. So we had a 1 on this XOR and also on this because of this carry bit, right? Just follow along the wires. Then we have this 1. Both ones at the inputs of the AND gate would give us a 1. Now we also have 0 and 1 on these AND gates, which 0 and 1 give us a 0. 0 and 1 in the XOR gate would give us a 1 because they are different. So the third bit of the result is also equal to 0. This is the third bit of the result, which is also equal to 0. And the next one, this one would be carried into the next stage. Again, 0, 1 in the XOR gate, they are different. We have a 1 here. This one would go here. We have a 1 and the carry, and the result of this XOR gate, we have 1 here. Now I just go faster. You could just follow along exactly based on the truth table of XOR and AND. We are not doing anything special. Just the truth table of the XOR and AND. So we have a 0 and 1 onto this AND gate, giving us a 0 here. 0 and 1, they would be different. So we would have a 1 here. Also, we have 2 1s at this XOR gate. So it get a 0 because they are equal. So actually, the fourth bit of both of them is also, of the result is also equal to 0. It's getting interesting, right? So next one, again, we have another 1. This one would go to, again, both wires. 0, 0, this XOR would give us a 0 because they are equal to each other. So we have a 0, 1 here. XOR gate based on truth table, if both inputs are different, then we get a 1 here. Now obviously we have a 1 here and a 0 here. This AND gate would give us a 0, and 2 zeros for this AND gate would have another 0. They are equal, so the XOR gate would be equal to 0. So next bit of the result is equal to 1. But the carry bit, so next bit is 1. Now look at the carry bit. This carry bit for the first time is equal to 0, carried to the second stage. So we have 0 here, 0, 0 on this XOR would give us the value of 0. Since they are equal, again they are equal, so we would get a 0 here. We have a 0, 1, 0 is enough for the AND gate to make the output equal to 0. We also have 2 zeros on this AND gate, another 0, they are equal, so we would have a 0. Both the result and carry bit are equal to 0. So I write another 0 on the result. So next one, we have a carry bit. This 0 on the XOR and on the AND, this just makes the AND to be equal to 0. We have 0 on this AND. Again, we would have this 0. The carry bit would be again equal to the 0. They are also 2 zeros equal to 0. This XOR gate would make it just equal to 0. So the next bit in the result and also the carry bit are equal to 0 again. So write the next bit equal to 0. So far we have just 7 blocks. I think next we get to the last block. So the carry bit of the last block is equal to 0. This would go to the 0 of this XOR gate. 1 and 1 in the XOR would give us a 0 because both of them are equal. 0 and 0 would give us a 0. They are equal again. So the last bit of the result is also equal to 0, but I haven't done the math of the carry bit. So we would have a 0 here. This 0 causes the AND gate output to be equal to 0. 1, 0 is enough. Then we have 2 1s on this AND gate, causing this to be equal to 1, because 2 1 and the AND gate, based on truth table, if both inputs are equal to 1, the output would be 1. Now XOR gate has 1 0 and 1 1. They are different, so we would have a 1 here. This is the last bit of the result, and then we have the carry bit of 1. So let me just first write down the last bit of the result, and then the carry bit, as you see, it doesn't go anywhere. This is the last stage of our calculation. It wouldn't act as any carry in as for any other stage. It's just the last stage. So we just write it somewhere. We say this is the carry bit of our calculation. This is the carry out of our calculation, which is equal to 1. So what the result has been, we just write this carry bit as the most significant bit of our result. You see, using 8 bits, we knew before that using 8 bits, the result can't fit. We need at least 9 bits to calculate the value of these two addition, which I think was 272. Let's see if the result actually works well. So this value would have the value of 256. This is the to the power of 8. Actually, this would be to the power of 0 if you know how to work with binary and decimal. So you would have 200 to the power of 8, which is 256, and this would be the value of 16, which is just 272, which, as you see, the result has been working well. We have 1 0 0 1 0 0 0 0. Since all registers are 8 bits long, so we say the result has been equal to 0 0 0. The result of the addition of this number and this number is equal to 0 0 0 1 0 0 0 0, and the carry bit is set. So we want to now abstract this circuit that we have created. I say I have an 8-bit adder with one 8-bit input called A, another 8-bit input called B, a carry in which I would set to I would reset to 0 whenever I want to do any addition, and I have an 8-bit output and a carry out. This carry out is set whenever the result cannot be fit into the 8 bits, which means whenever the result is bigger than 255, which in binary would be just 8 ones. The result like 272 that we just made the example of. Now, one question that you might ask is that, or actually let me just first talk about all the instructions that are implemented or are using this underlying hardware for doing the addition in the AT85 microprocessor. These instructions are like this: add A, B, C, D, E, H, L, and M. They mean that I want the values, the content of the A register to be added with one of these registers, or this would be the memory that the HL register pair is pointing to. Now the opcode for add is equal to 10000, and then 3 bits which specify the other operand, the contents of the other register that should be added to the register A. So register A, like always, is one of the operands. Now, and we know that the registers in AT85 microprocessor have these combinations. If all of them are 0, it means the value of B. If I have 17 zeros, then it in hexadecimal it is 80. It means that I want the values of the A to be added with B and the result to be saved in the register A, and so on until we have 87, which means that I want the value of the register A to be added with itself and obviously saved in the same register. So imagine, but what do I mean that we want to do this? Imagine that we have 80 in the hexadecimal, or this pattern of 170s in the IR register. What the AT85 microprocessor does is that it knows that this pattern means that it should load the value of the A register in one of the inputs of our 8-bit adder and the value of the B register in another input, and then the carry in should be cleared to 0 to do the addition, and A plus B would happen, and the result, the A right now, let's say the value is 1C in hex, which in binary would be 0 0 0 1 1 1 0 0, and B would be 0 0 0 1 and 4 zeros. So it would just load the A register, this content, in one of the inputs exactly like what we did, and this would be done in the other one, and the addition would happen. It's just the computer would do it, all of them, so faster than what we did, but you could just follow along to just understand more about how the carry bit, which the important factor, as I said. Now for those of you who took my other course, you might say, well, this is just a repetition of what we learned before. But as I said, the goal for creating any lecture is to give you some intuition. So the intuition here was that instead of just explaining about what flag register would be, which is actually the main goal of these set of lectures, I decided to just tell you how or where it comes from. So 8085 saw this pattern of zeros and ones in the IR register, understood that it should add the value, the content of the A register with B, loaded the contents in the A register, which is this pattern of zeros and ones, in one of the inputs of the OR 8-bit adder, loaded the contents in the B register, in the other input of OR 8-bit adder, cleared the carry in to 0, and then saved the output of the 8-bit adder here inside the A register again to execute this instruction. These were the 8 of the instructions which uses the underlying hardware that we explained here to carry out the addition. And then we have other instructions as well. Other instructions for addition would be like this. So would be ADI byte and ACI byte. One of them, as I in 8085, always means immediate. This means that add the immediate byte here with the contents of the A register and save the result in the A again. And the opcode for it is C6. For example, if in the IR register we have C6, which in binary is 1 1 1 0 0, and then 6 would be 0 1 1 0, then 8085 microprocessor understands that it should just read the next byte in the next memory cell. Let's say that what we have written as our instruction would be this, and just 1 0 0 1 1 1 0 0. So this just means 9, and this is C. This means that I want the value, the content in the A register to be added to the value of 9C, and the result should be put inside the A register again. So instead of loading one of the register in the other input of the 8-bit adder, it just loads this value in one of the inputs of the 8-bit adder alongside the A register, which always be one of the inputs of the ALU, which if I want to show it to you at the first lecture that we explained about the architecture, I think it was this one, we said at one of the first lectures, well, here if you could see them, this was the ALU, right? In the ALU, we said that in the ALU of 8085 microprocessor, we said that one of the inputs always comes from the 8-bit A register, and another input would come from the temp. So when in the IR register, when for example we have a value of 80, what this 80 in the IR register means, this is the IR register, which was again 8-bit. So if we have 80 here, 80 in hex, the 8085 microprocessor knows that first it needs to copy the value in the B register inside the temp by putting those value onto this 8-bit internal bus, and then this 8-bit internal bus would be copied. As you see, it could be copied inside the temp register, and then A is always one of the inputs of the ALU itself, so these two would be calculated, and the output of the ALU again would be put on the 8-bit internal bus, and this would be again saved into a register. And the carry bit here, if it is set, these data would be written in another 8-bit register called flags register. This would be one of the 8 bits of the flag register. We would talk about other bits in the flag register as well. Now, before we end this lecture, I just wanted to show you one more thing, and that's about the, let me bring this up, that's about the carry in. You might say, well, if the carry in is equal to, always we set this equal to 0, then, well, why are we even using it as a variable or talking about it? We could just always clear it to 0. Well, the reason is that we could use the same circuit for doing the subtraction. Instead of creating another circuit, we could just use the underlying circuit for doing the subtraction, which you would see in the next lecture.